My name is Ian Hojnicki. I'm a user interface architect in the user interface group. That's a lot of user interfaces. And today I'm going to talk about our high resolution support in 12.1 and what that means for notebooks and in particular working with images, because that's arguably the most drastic difference. But just really quick to get started, we got to go over a couple of terms that I'm going to use, and in case you're not familiar with them. One is a desktop publishing point, which is recognized as being 1/72nd of an international inch. And this dates back to really old printing days. A lot of the times people will just shorten that to point. That is exactly what I'm going to use, because even though our documentation says printer points, it's still one word too many. The other key term is dots per inch and pixels per inch. I won't take a stand on which one. It's kind of like Vim or Emacs, but they're both trying to convey the same thing, which is basically they're trying to describe how many elements there are per physical space. A lot of the time dots are used with printers, and back in ye olden days, OSs would refer to them as dots still. PPI is a little bit more modern, tend to be used more for raster devices and bitmaps. And as you can see down the bottom, depending on the density, you can pack more pixels per space. They're all the same size, but the data that you can represent inside of them is different. The one on the right is the highest quality that my inkjet printer can do. The stuff in the middle is more like 4K-ish. Stuff at the lower left is more of the old standard stuff, 1080p and things like that. So what exactly does high DPI mean? And a lot of the times, if you ask that to somebody will say, oh, that means it's 4K. And if you're really into it, 5K or 8K. But really, in the end, the actual designation of it really doesn't matter. From a software developer's perspective, this is all about supporting resolution independence on any device. The desktop front end has always had some form of resolution independence, because what you saw on screen, and what you print to paper are two totally different things, and yet they're WYSIWYG, they match. But in this day and age, it's far more common to have a vastly wider range of devices. And I did a quick sampling earlier in the week. Working from home, I tend to end up using these devices quite frequently. My Mac, my 13-inch MacBook Pro is, physically it's 227. That's not actually what Apple will run it at, but that's what it is. The Windows devices, the two really low ones are my TVs. And then the hundreds and higher are my 4K and 5K displays. That's really difficult to work with, because devices are all different. So OSs will like to coalesce them into buckets, which are typically referred to as logical DPI or PPI. Once again, I'll use these interchangeably. The Mac, because of the Mac actually runs at 144 because it's Retina, and that actually works out to be about right for what they're running it at. Windows gets, my Windows laptop gets bucketed into, either 96 or 128 or 192. So they all kind of coalesce to this much wider range, gets funneled down into a much smaller set. And it's important to know that the desktop front end works exclusively in logical DPI. And there's reasoning, and that's tweaked. It simplifies matters in a lot of ways, but it also means that if you're like, well, I told it that I want it to be 2 inches and I took my ruler up and it's not 2 inches, I always have to ask the question, well, what are your settings? Because you can drastically alter that relationship. Which brings me to probably the very first point of 12.1, which is the very first question I get asked is, why does 12.1 look so different if I'm on Windows or Linux? And the main reason is this. In 12.0, the desktop front end was not resolution independent completely. And so it classified all desktop displays as being 72 dots per inch. Translation, if you asked for a font of 12 points and we drew it to screen, it would, the EM square of it, which is the space that a character could take, would be 12 pixels. And so if you were on a device where you didn't have a 72 DPI monitor and it was a much higher res one, the OS would do bitmap scaling to bring it up to size so it didn't look really tiny. And you end up with this really nasty blurring effect. So, at 1x, which is 72 there, it would be nice and crisp, but as, the density goes up, it would blur out. Now, this is approximate. It's not really fair. It's not that bad looking, but it is blurry and people complain about it, rightfully so. So we fixed it. So, this is great. The front end now understands, what the device's DPI setting as reported by the operating system. And if you ask for a 12-point font, the EM square is almost guaranteed not to be 12 pixels. But the nice thing is that the font size of Cambria 12 in the front end should match Cambria 12 in Word or Cambria 12 in, I forget what LibreOffice's name, Writer. I think it's called Writer. They should match. And no matter what density you have, that text should always look amazing on it. So this is all great. This is great. I have text that's now clear, and things always look good. But Ian, you still haven't answered the question of why does 12.1 look different? And the reason behind that is that, because pixels and points are no longer a one-to-one correlation, and we actually work off of what the DPI, what the OS is telling us, things are now going to match what they were actually spec'd to be. We actually respect the data that's come back. And while this entire this entire slide is talking about font sizes is not the only place where points are actually used in the desktop front end. And where are those actually being used? Turns out to be just about everything. We have a handful of exceptions, which are in font relative units like EMs or line heights. But for the most part, all the size and margin specs are in points. So if you spec an image size, as listed here, of 40 by 40, and you expect it to be 40 pixels, it's no longer going to be 40 pixels. This is applicable to window size. So if you asked for a window to be 400 by 300, it is not going to be 400 pixels by 300 pixels. It's going to be 400 points by 300 points. And if you're on that 168 DPI display, that will be a much larger number. We do it for directives, all the absolute dashing, thickness, point size. All of those are actually in points. So if you were asking for a line to be 1 point thick, expecting it to be 1 pixel thick, that's no longer going to be the case. And then, of course, mouse position, touch position, connected displays, any function that would return you something in some kind of coordinate, those are all in points. And the reason for this, well, I mean, we're a document, the front end works in documents. So it's not crazy that we would have worked in something that isn't pixels. But it's also been this way since 5.2. It was fun the other day. I actually brought up the help viewer from 5.2 to look at the docs, and that was actually a throwback experience there. So a lot of different ways in which the coordinates that you might have assumed had been one and the same are no longer necessarily the same thing. So the next question that a lot of times I get asked is, well, okay, that's great. If you're telling me I have to work in points, but I have pixels, what do I do about this? Well, I mean, it's really simple and straightforward. It's just a simple scalar. The key thing is you have to know the density in order to be able to get back and forth. Now, working with Windows, that's really easy. That's our responsibility to deal with. But there's other things that require a density, like, for instance, images. Images are just, a two-dimensional array of pixels, but they also have some metadata in them that tells you approximately how big that image is supposed to be. And we actually have an example here from the example data, of some apples. And if you look at the dimensions for said image, it's 2,700 pixels wide, which is actually about 2/3 of this monitor, maybe, roughly somewhere in there. And its image resolution, the density of this image is 300 by 300. So in points, that actually works out to be 648 by 432. And that's roughly what that displays as on screen here. So given pixels and the image resolution, we can automatically figure out what its natural image size should be. And based on, depending on all the data necessarily, you can tweak what that visible size is going to be solely based on the density of the image itself. We also have image resolution, which you can spec as part of export and rasterize. So you can get back to the 12O behavior by speccing that you want the image resolution to be 72, which is what the front end used to be. And if you ask for something that was 81 in each dimension, you get back something where in pixels and in points, they're identical. But now you can also do something more along the lines of, this is more accurate for my setup, where I want the exact same plot at the exact same, image size, and I get 2.667 times more data out of it, where it's now 216 by 216. And of course, you can go further. Obviously, this is my printer. This is my inkjet running at its default quality. And you get something back that's 405. But all of these all have the same physical dimensions. They're all 81 points for each side, which also illustrates a good point, which is image resolution is a lot like plot points. You don't need to go crazy in order to generate a nice looking image. Like, I've seen some examples on Stack Exchange where it's like, oh, well, I'm going to throw image resolution of 5,000 in there. Well, I'm not going to do 5,000, but I'll do 2,000. And 2,000 is 100 times more data, or 100 times more pixels, for the exact same visible space, which means you're generating a lot of data that technically isn't even going to be visible because it's being thrown out. Well, it's not thrown out, but it's blended. And so if you don't need that fidelity, you don't need to jack up the image resolution that high. Now, if you're doing something where I'm doing some pre-processing that I'm going to push down to something else later in the stack, and I need it to be ultra, ultra, ultra dense, well, that's fine. There's nothing wrong with that. But of course, that's also, if you're generating something that's going to be seen on screen, it's probably not the most optimal way to go about doing it. You're definitely using a lot more resources for no real immediately visible gain. So we have image resolution for rasterize, and that's great. You can start playing around with these things on your own. The problem kind of comes in that, well, I have to keep speccing all of this into rasterize. It'd be really nice if I could kind of, set it once and for batching, for batch jobs. So we have $image resolution, which by default is automatic. And the automatic case basically means ask the front end to render something at the highest resolution for my display, or for my machine, for my setup. And this is done primarily because of the fact that, we had a couple of choices that we could have made. We could have left it alone and left it at 72 and then asked Rasterize to make ugly pictures for the rest of time, which, yes, it would have been consistent with what it did before, but then also it's a really bad experience going forward when, the industry is trending towards denser displays. I didn't want it to be a fixed cap value, because then it's inevitable that you're always going to blow by a fixed cap. So in the end, we came to this compromise of let's just do it for the most reasonable that's currently valid or currently would be used. And of course, once again, you can totally change it if you so desire. If you want complete control, you got complete control. It's just about we're trying to make the defaults convenient for everyone who might not necessarily care about these things. Once again, because this is a global, there's always the problem of what if there's two people trying to do the exact same thing, but slightly differently. So normally we recommend using block to prevent it from leaking out. So that way, you can still get what you're looking for, which is something different from the default, but it also at the same time doesn't overflow into everyone else. And the nice thing about all of this is that this round trips. So as long as you're using a lot of the most common image formats, export will write the metadata in for the density, and import will bring it back in, and it'll get back into image, and it works its way back into the front end. So you can work with these things and they expect consistency across the board, which is kind of cool. Downside is the second, maybe it's not the second most question, but it's certainly up there, is why is my bitmap so small now? And as a great example of this, is the one that comes out of Wolfram Alpha for this case with Zebra. And as you can see, it's really tiny. In 12.0, it wouldn't have been. And the reason, of course, is that, it's 150 pixels wide at 300 pixels per inch. So it's a half an inch wide. That's why. If you're interested in fixing that, obviously you could just wrap image around it and set image resolution to be 72. And that would restore it back to the old size that you're most used to. But this is working off of the metadata. So, metadata for these things is important. And if it's not spec'd, I should mention that if image resolution was omitted, like you had something pre-version 12.1, that the front end will treat it as if it was still as 12.0. So it would go, okay, the natural resolution for this is 72 then. So it displays at the size that you were expecting it to, because it can't make an educated guess that what the density of it would have been. The next question that comes out is typically, why is my bitmap blurry? And the easiest answer to that is normally your image isn't running with the same density as your display. So for instance, here's plot. We have a very, very high desire to keep plot lines really thin and really sharp. So it's really thin, it's black, it looks nice and crisp. You go through and rasterize at a much higher resolution, right? All those pixels have to go somewhere, and it's twice as big, but crammed in the same physical space. And so therefore, what happens is you have two choices. You can either throw pixels away, which is generally bad and looks terrible, or you can blend them all together. And blending them together is what we do. That isn't cheap, by the way. So if you're like, oh, I'm going to have my 5,000 by 5,000 and squish it down into a really small, it's not cheap. You're doing a lot of work for not very much. You don't get very much out of that work at the end. But nonetheless, that's exactly why that happens. Next biggest question that tends to come up is I had this thing and I'm trying to use graphics primitives with it, and none of this stuff works. So good example of that, here's an image that I have. It's 504 pixels wide, which is 121 points wide. We're going to call it roughly around in there. And I'm going to take, and I'm going to drop spot into the image, basically a quarter of the way up and a quarter of the way in from the left-hand side. And lo and behold, where's my spot? And well, okay, so what happened here? Well, what happens here is that the front end actually doesn't work with image, it works with boxes. So there's a box that represents an image. And that box has, pixel data, and it has a range specification for it. And that range specification is used to translate between graphics coordinates and pixels. So as you can see, it's not like the front end has it wrong. The dimensions of the pixel data is right. It's 504 wide. They flipped, but they're 504 wide. And the range spec is the point spec. So, and then if you look at the plot range for said graphic that comes out of it, it's the point spec. So if you were to seeing that this was a quarter of the way through, you take a quarter of 504, and it's definitely bigger than 120. And a quarter of 378, it's definitely bigger than 90. So my red disk is actually off the screen or off the image itself. So, okay, what can you do about this? Well, I mean, the two easiest ways are really, especially for the synthetic example, is one, to use points. The conversion is easy enough because the density of the image. You can do all of this yourself without any real work. And of course, now your spot, the red spot is now back where it should be. You can also use scaled. I mean, because scaled is really easy because now you don't even care what the coordinate spaces are. You just know it's a quarter of the way in. Obviously, that doesn't always work. Scaled coordinates isn't always right, but certainly you can, the transforms are simple enough. If you want it to be placed in points or in pixels, the front end isn't going to do that for you automatically. You have to do the work to do it. But once again, these are just transforms to switch coordinate spaces. So it's theoretically possible if you wanted to, but it's much easier to just do and convert it into pixels or use scaled, or sorry, points or use scale. But this actually came up enough that I actually talked with Brenton some and got it added into his linter. So you can actually run through a bit of code, and it has a rule in it that will go through, and if it sees image dimensions on the right-hand side of image size, it's going to flag that as potentially being a bug, and you should be looking at it. Now, the confidence level on this is not the default, and because there is a case where this actually is correct. So that's why it's a little low. I'm going to talk about that case here in a second. But certainly, this is a good way to help you find out places where this assumption that pixels from an image directly map to image size, where that is now no longer the case. And if you're interested to know more about the linting stuff, you can check out Brenton's talk last year from the tech conference about finding bugs, which is really good. And he had a workshop earlier this week where I'm certain that must have come up in, so that you can totally check out. The last interesting example, the one I want to bring up, is using image as a replacement for calling rasterize, because wrapping something with image is really convenient, and a lot of people have done that. But there's an interesting quirk with it, which makes it hard to recommend people to use. Now, on Zoom, I don't know how well this comes through, but the thin line is kind of important. So the left-hand one is the graphics primitive itself, the raw graphics primitives. The one in the middle is the result of wrapping it with image, and the one on the right is calling it with rasterize. Now, the one in the middle is all grayed out. And the one on the right looks way more like the one on the left. Now, why is that? Well, using image with image size is effectively like calling rasterize, where your image size spec gets passed into raster size. and the image resolution is fixed to 72. Now, I didn't actually look at how it's implemented. So this is not a direct, oh, this is how it's implemented. I have no idea. But this is the actual implications of what it's doing. So that has some interesting things, because now if you start messing with image as a wrapper, it starts doing some interesting things that you're probably not expecting. One, I asked for this graphics primitive to be a disk that's 81 by 81 points. And I'm going to give it an image resolution. I want it to be at 168, which is actually the density of this display. And if I ask for the image dimensions of it, well, it's my 81 pixels. And that should be obvious looking above. The image resolution is 72. There's a one-to-one correlation with it. Okay. But now if I were to ask for the same thing in points, which I would have expected if it was rasterized at 72, it's not 72. It actually reports as 168 because I told it it's supposed to be 168. So now I get a much smaller point size. What's effectively happened here is the image resolution of 168 was overriding what it actually rasterized at. So you can get yourself into the state where you have a result that is half in, half out. And basically, you know, if you don't care about the end result of what you're rasterizing is maybe using it for some data step, and it does what it needs to do for you, then it's fine. But if you care about, you know, oh, I need it to be at this resolution, and I need it to be at this size, and I need all this stuff, image as a wrapper isn't the way to go. Rasterize is the way. You get exactly what you want in a consistent form every single time. So based on some of that, once you start working with points a lot in places and thinking of them as points as opposed to pixels, there's a couple of interesting things that come up immediately as being, well, maybe these aren't exactly the smoothest things. It'd be really cool if we could do something about it. And, you know, I'm putting some of these out here. None of these are in 12.2, sorry. But these are a handful of things that we've been tossing over, thinking about, and it'd be really good to get some feedback on which ones you think are more important than others. So, forgot to close that. So the first one is obvious. The most obvious one is quantity. You know, who wants to think necessarily, if I have to think of things in physical space, why am I thinking of them in terms of this arcane 72nd of an inch kind of thing? Why can't I think of it in much more natural things? And so getting units like centimeters, inches, and millimeters. This build actually does this. I have a build that's my own personal one. This build can actually do this for image size, which is actually kind of cool. But I mean, it should be applicable to way more than just image size. Typographic units, you know, I expect that to be in there because TWIPs are used quite frequently. Picas are used some. I'm sure there's a handful of others out there that would be interesting to do that I haven't even thought of yet. Relative units is actually probably the most interesting one to me, because it allows you to size things according to the ambient font, which we've actually done. We've actually internally done for a handful of things. If you saw John's talk earlier, he was talking about using template box for updating the boxes, the typesetting for RGB color, and the boxes for RGB color are trying to do this, and it would be way cooler if you could just go, oh well, it's just I need it to be this size relative to the font, which would be kind of cool. DPI itself is kind of an old, you know, I mean, it dates back quite a ways. You know, there's other alternatives. I mean, obviously the most natural one is, well, if it's inches, why is it in centimeters? Why is it metric? So being able to spec that metric. I don't know if you could convince me that dot pitch is a good idea, but if you feel strongly about it, I'd certainly be interested in hearing your case for it. You know, once we start talking about, you know, oh, the problem of I rasterize it as a specific resolution, then it moves to a different place, and now it might not look as ideal. I want to be able to compensate for that. You know, then we start talking about multi-image support. which is most often in 2D, 3D world. It's most often referred to as bitmaps, level of detail in one single image, which is really cool. We've been talking about that for 3D graphics anyways, but in 2D, it now actually becomes a big deal because I thought about doing this for notebooks and saving multiple, we cache expensive graphics that take a long time to render, we cache them. And it'd be really kind of cool if it actually could cache multiples of them. So that way it always looked right no matter where you went. So that's kind of cool. Another way of doing this is the thing calling dynamic assets. Basically, it's a way to load external data in situ. That's the simplest way to put it. The more obvious example is like if you look at like the new opening cloud dialog, like those buttons that say OK and cancel, the OK one is red and has stylized, and the cancel, it has a different style to it altogether. We use like a precursor of this internally today. And we've been talking about, formalizing it and bringing it up so it's well documented and people can use it themselves. And this is a nice way, once again, to be like, oh, I need this image, but I want the one that's specific for this exact environment, which is kind of cool and be useful to use. And then I'm going to guess a lot of people said, when they saw this come up, because I don't understand the correlation between the two. High DPI support, resolution independence, I should say, is actually a prerequisite in order to get gesture handling on touchscreens on Windows specifically. Mac, that was probably already there and it would have been fine. Linux, I'm not 100% sure on that one, but certainly getting Windows to do it, we had to get resolution independence, which is, kind of cool. So people have been asking for it. But now that we actually can get to the point where we can really, build this out, it'd be nice to know how many people are actually interested in this. Certainly, getting supporting for pen, that's come up, and touch, is an interesting thing to deal with as well. So that's it for my talk. I only ran 3 minutes long, so that's pretty good. I consider that a win. I'm going to go through the chat now. We'll keep this on and I'll just read these out. Well, maybe, I don't know what's easier, best on that. But most definitely, if you think of something afterwards, we're doing an office hour in like 2.5 hours, where it's me, John, Lou DeAndrea, I think Parth will be there too. So if you got questions about the front end, why it does something, I really hate this behavior, why haven't you guys bothered to fix this? Totally bring it up at that point as well. And cool, so thank you very much. I'm gonna go through and go through the chat and hope you guys have a pleasant rest of the day.